balanced job bounds. So we saw before those R of n bounds, right? R of n is greater than or equal to D, but there is no real lower bound. X of n is less than or equal to 1 over D max, right? At but then what is the corresponding, right? Bound on the other side. So that was what was attempted to solve. I guess this is back in the 70s or early 80s, with the help of this so called balanced job bounds, for which I had to flip back quite a few pages. Okay, so what is a balanced job system, right? So there is a definition for that. So a system with technically no bottleneck device, there is kind of where all the demands are equal, right? A system where all demands are equal, right, for all the devices. This is a balanced system. So that is the definition. So all the D's are equal, DIs are equal. Therefore, there is no single bottleneck device. Basically, all devices are bottlenecks, right? Whereas if there is one device which has D max, then that tends to be the one that dictates your throughput, right? Okay, so consider, right, a balanced system such that so this is a system where there is no terminals, right? Only your CPU, disks and so on. Okay, this is your central subsystem as you call. So let us not yet look at. So there are m devices in this queue, and the total demand is D, right? Remember D was sigma Di, and therefore Di equals D by m for all I. So we now remember our Ri of n, right? So Ri of n is basically Si into right. This is from before, where if there are in the ith queue, if there are n minus 1 customers already waiting, then the demand that response time for the nth job is just this one, right? We have seen this before. Okay, so since all the queues are equal, that will have to, right. So since all the demands are equal, the expectation is that all the queue lengths will be the same. So Q of is simply where Q of j is the total number of jobs in the central subsystem. So now R of n is Ri of n into right. This we know from before. This again we write this as Vi into okay, yeah. So this is our Ri, right, Si into 1 plus Qn minus 1 by m, and Vi Si is our Di, so that is that, and this is now equal to remember Di is defined as D by m, right, so this is so since there is no need for I anymore here, simply multiply this whole thing by m, right. So this is D into 1 plus Q n minus 1 by, this is your R of n, right. So for a balanced system, R of n equals D into 1 plus Q n minus 1 divided by m, which we can again expand this as D plus D by m into Q n minus 1. Okay, that is our step 1. Okay, this is a long derivation. Okay, so this is part 1 out of the 4 steps. Okay, so this is fair enough. So now let us assume that, so here we have a shared system, right, there is a central subsystem that is shared among these n users in the system. So let us look at a system where let each user have okay. So there is no queuing as such here anymore. I am giving like a PC that is given to every each of the n users, right, in the system, total of n users, out of which I am giving each user their own system. Okay, so there is no queuing here, right, this is like a zero queuing system because everybody has their own system. So what is the total time spent? So this user spends D times, right, D in your central subsystem, this is your CPU plus right, CPU plus disks, and then Z in your terminal, right. We saw that D is the total demand made by this any job on the entire system, so therefore D and then Z, right. So therefore if you look at this, each user has a probability of of being in the central subsystem that is equal to, so what is the probability that a given user will be in the central subsystem? Either you are in the central subsystem running the computation, or you are in the terminal subsystem where you are simply processing and idling, right. So what is the probability? D by right, that is a probability. Total time, right, is D here, Z there, therefore the given probability is just that. So then if you look at our original definition, right, so we have a system with n users, out of which some of the users are in the central subsystem, others are in the terminal subsystem, right. So the total number of users in the central subsystem is given by your Q of n, right. Q of n is the sum of all the device queues. So therefore the total number of users in the central the queue basically for processing either disk or CPU is Q of n, okay. So now, so Q of n by n, so out of the n users, Q of n are in the terminals or are in the central subsystem, the others are in the terminals where there is no processing, simply right delay center. So Q of n by n represents what? Probability that the user is in the central subsystem, right. Out of the n users, Q of n are in the central subsystem, the remaining are in your terminal subsystem. So Qn by n is the probability that a job, right, or is in the central subsystem in the original system, in the original shared system. Right. In the original system, Q of n by n is the probability that the given job will be in the central subsystem. So which will be more, this one or that one? This is the probability when you have nobody else sharing your system, right. So the probability for queuing will be more in the other system, right. The probability that here there is no queuing at all. So the this therefore Q1 by n should be greater than or equal to d by dt, right. So one system with queuing, one system without any queuing, right, and therefore this should be your lower bound. We have to be at least as large as that depending on the value of n. If n is very small, n equals 1, then there is of course no queuing in the system too. N becomes larger, then the probability that you are going to be queued is larger. Therefore the probability of being in the central subsystem is greater than the probability that you will have in a system where you have your own unique system assigned to you. Okay, so that is part A. Time. So then we will go to part B. So now we say that instead of having every user having their own system, they still have the same system, but it is n times slower than the original system. So the capacity of this new system that so this is one kind of system, right, this gives you this bound. We look at a different kind of system where every user has their own individual system, but that is n times slower. Therefore the effective capacity is same as the original system, okay. So let each user means each device service time S of I, right, is going to be NSI in the new system, right. That is what it means by being n times slower. If I had SI service unit, the SI service time in a particular device in the original system, the new system I have n into SI as the service time, that is what I mean, right. So therefore what happens if your DI is now n into SI into VI, so therefore all the DIs become multiplied by a factor of n, right. So therefore right, so all the DIs become DI dash becomes n into DI, right, in this new system, because each device is n times slower and therefore SI is also slower, and but your VI does not change, right, the number of visits to every device stays the same, therefore it should be n times, right. So the total time taken to process will be n times the original time, that is what, right, okay. So therefore time in the CSS equals n into d. So what is the probability that a job will be in the central subsystem is nd by nd plus z, right. nd is time spent in the central subsystem, z for terminal processing. So therefore this is another bound for the same probability of finding a job in the central subsystem compared to the original subsystem. Okay. So will the, for the original system q by n, right, qn by n in the original system, will this be more or less than that? This is n times slower system, right, whereas that is n times faster. So therefore this should be less than or equal to this, because the system is n times slower, but there is only one user in the system at a given point in time. The other system is n times faster, but you will have in the worst case all n users in that particular system, right. Therefore this should be your other end of the bound. So therefore combining these two fellows, we have so for a balanced system, this is here, this is one step, right, we have some more steps here. So we will now write the same thing with n minus 1, right. So replace n by n minus 1. So what do we have, d by d plus z is less than or equal to q n minus 1 by n minus 1 divided by n minus 1 into d divided by agreed with that change. Then we will multiply this entire expression by n minus 1. So what will we have, n minus 1 into d divided by d plus z is less than or equal to q n minus 1, which is less than or equal to n minus 1 into n minus 1 into d divided by n minus 1 into d plus z, right. So here you multiply by now you add d by m, sorry, add d and multiply by d by m. So rather other way around. So multiply first everything by d by m, then simply add d for this entire expression. So what do we have, so this is d by m into n minus 1 into d divided by d plus z. This is less than or equal to right, just routine algebraic manipulations. So multiply by d by m first everywhere, then add d to both sides. So what do we get now? So what is this expression finally, r of n, right. So that is what we wanted to get to. So for a balanced system, your r of n is given by these bounds where all the demands are equal and therefore all the q lengths are equal. So for this system is given by this expression. That is step 1. Now we have to do 2 more experiments to finally come to the bounds that we want for an unbalanced system. For a balanced system this is good enough, okay. Then 2 more horrendous trips later we will come with some better bounds. In fact you will find that the bounds are actually really much stronger compared to what we saw before, okay. So I am not sure how much enthu you have for knowing those bounds, but we will anyway proceed with those bounds. But it will be useful at some point in time when somebody says here is a queuing network, just give me the bounds, I do not care about running this MBA and all that stuff, just tell me what the bounds are, right, give me better bounds. In that case you can simply just run this formula in 2 seconds, tell them this is the bounds, and that is enough. You do not really need to know the exact value for the exact values are not needed, just upper lower bound which is fairly close to the actual, after all this computation that we do with xn's, right, and all that, we do not have to do that if I can actually use this. That is the reason for going through this, right. We did all these calculations and finally find that it can give you a fairly narrow set of bounds which is adequate in most cases. If you are talking to your customer, right, customer says tell me what will be the delay for this particular system, you are going to sell them your web processing system, some transaction processing system, and then that guy says okay there are so many steps in this transaction, give me bounds on this performance, and then you do not have to go, oh let me write my Yaxim code and come back to you 3 days from now, right. You do not have to do that, or let me check my spreadsheet to do this MBA calculations and come back to you. No, you can take this as a shortcut and get back to you. That is the reason for going through this, right. Okay, so we will stop here, we will come back and then use these 2 sides of the expression to give better delays or better bounds for both R of n and then x of n.